In this video, we'll be giving an overview of some of the forensic and review capabilities of our new system. But to help put all this into perspective, we'll first spend 10 seconds reviewing some of the underlying technology. In our approach to additive manufacturing, a wall of metal is created layer by layer by melting an incoming wire with a high-energy electron beam. The path of the wall is managed by smoothly moving the stage underneath the work area. Through granular control of the beam's power and scan pattern, we can not only melt the wire, but also acquire high-resolution images of the deposition as it happens and make precise measurements of how everything is proceeding at any moment during the build. This combination gives us the opportunity to employ a high-speed process feedback loop where the system will automatically and autonomously adjust control parameters to ensure a consistent result. We'll cover the mechanics of that in a separate video. For now, though, we'll focus just on the data collection and replay capabilities. Every measurement acquired during a build is recorded in a database and is available for review. In this example, we'll look at a simple shape that represents a 21-hour job. Once loaded, you can see that we have access to all the blunt metadata you'd expect, such as number of layers, start and end times for the build, etc., etc. Of more interest, however, we can actually review any part of the entire build. With this panel, we can look at any of the scanning electron images taken during the job. Here we see a 256 by 256 pixel image, representing about a 5 by 5 millimeter field of view. You'll notice where the wall edges are from earlier layers, the position of the incoming wire feed, and even the shape of the molten pool of metal that trails behind on the wall as it moves along. As we move this slider along the timeline of the 21-hour effort, we can quickly pop to any point in time. For this example, we've made measurements 10 times a second, and we can replay the images at the same rate, giving us a nice movie of the depot. Well, let's put that away and play with another view. As you'd expect, we can take any metric gathered and make a line plot of it. You may have noticed a moment ago when watching the images that the location of the incoming wire would wiggle a little bit, so we'll examine that. It's relatively easy for us to know the position of the wire with respect to the field of view, which we express as some distance off-center. For the bulk of this run, it generally stayed within 1/10 of a millimeter from the center, but every once in a while it would stray up or down a bit. We can zoom in on those situations like this. Notice how for a short period of time, the wire was more than 0.2 millimeters from the center line. Great, let's put this away and play with another view. Here's a 3D representation of the full build as reconstructed from stage position information we gathered. And of course, we can do all the things you'd expect, such as moving our view around and zooming in or out. We can also click on the graphic to place a cursor over specific locations, and we can see the exact coordinates of the build and when the location was visited during the job. You'll notice that there is some coloring to parts of the display, some red stripes and some blue stripes. These correlate directly to locations where the wire position strayed out of acceptable limits, as shown on the legend. So, let's see how these views work together. Changes to the timeline slider or cursor on one display are immediately reflected on the other displays. This allows us to focus directly on data of interest and explore the full context. If I'm interested in this part of the job where the wire was coming in too far off center, we can see exactly what part of the build that relates to, and can even back up a little and replay the image scans for that area. For all of this, we used wire position because it was easy to discuss and demonstrate, but the same options are possible for any and every other metric we gather, such as the size of the melt pool or width of the underlying wall that was deposited. So why do we do all of this? The E-beam is perfectly suited for making precise in-situ measurements in a harsh environment that prevents traditional methods. The entire data set provides unparalleled insight to every aspect of the job and the part that resulted from it, and the volume of data is ripe for analysis and process improvement through various machine learning algorithms. Most importantly, though, and something we've only hinted at in this video, is that all the in-situ measurements we're gathering are part of a process control loop that allows our system to dynamically adjust all the control parameters, beam power, scan pattern, stage and wire speed, in real time to guarantee a repeatable and anomaly-free result, job to job, week to week, complete with a full data set to document it. Anyway, we hope you found this interesting, and if you have any questions or comments, please let us know. Thank you for watching.